When we think about a line segment, we naturally assume that the amount of space it takes up, its physical length, is directly tied to the number of points inside it. It seems obvious a longer line contains more points, and if you shatter a line into a disconnected mist, you reduce its size. In point set topology, we separate these two ideas. We count the number of points in a set, which is its cardinality, and we measure the geometric length that the set occupies, which is simply called its measure. But the rules of real analysis allow for mathematical structures that sever this correlation entirely. We are going to strictly prove the existence of a set that contains the exact same uncountable number of points as the entire infinite real number line, while taking up absolutely zero physical space. This topological anomaly is called the Cantor set. By constructing it, we see that human geometric intuition fails when trying to map the infinite density of the continuum. To understand the Cantor set, we first need a baseline for infinity. The real number line stretches endlessly in both directions, and its infinite density of points is known as the continuum, denoted by the letter C. This document illustrates a concept called bijection. A bijection is a mathematical mapping that pairs every element in one set with exactly one unique element in another set, leaving nothing out. When a bijection exists between two sets, it proves they share the exact same cardinality. We can use a geometric projection to show how a finite open interval compares to the infinite continuum. Take a finite line segment, bounded by A and B, and bend it into an open semicircle, resting tangentially on the infinite real number line. If we place a point at the center of that semicircle and draw straight rays sweeping outward, each ray passes through the arc and continues until it strikes the infinite line below. Because the bottom line extends endlessly, every single point on the finite arc maps to exactly one unique point on the infinite line, even at extreme angles near A and B that project far out toward infinity. Every point finds exactly one partner. Therefore, the cardinality of any open interval is identical to the entire infinite space of the real number line. This establishes our first rule of cardinality. Placing finite boundaries on a line does not restrict its infinite point potential. To construct the Cantor set, we start with a closed solid interval from 0 to 1. The strict recursive rule is, at every step, we locate every continuous segment and completely remove its open middle third. For stage 2, we apply that identical rule to the two segments we just created. Removing their middle thirds leaves us with 4 even smaller pieces. As we move to stage 3, stage 4, and beyond, the segments fracture into exponentially smaller fragments. We then carry out this process a countable number of times, pushing it to the limit as n approaches infinity. The points that survive this infinite sequence of deletions, the residual structure, form the Cantor ternary set. By systematically fracturing the space, we isolate the mathematical dust of pure points from the geometric length of the line itself. To understand what is left over, we calculate the exact physical length we just erased. These lecture notes track the total measure removed. In stage 1, we subtracted exactly one segment of length 1/3. In stage 2, we removed 2 segments of length 1/9. In stage 3, 4 segments of length 1/27. This forms a specific pattern known as an infinite geometric series. When we resolve the formula for the infinite sum of these terms, the fractions collapse perfectly. The total length of all the removed segments equals exactly 1. We started with an interval measuring exactly 1 unit in length. We subtracted segments totaling exactly 1 unit in length. The remaining measure must be 0. Geometrically speaking, there is nothing left. A structure with a measure of 0 cannot hold any physical space. If the length is 0, what points actually survived the infinite removals? To answer this, we translate the interval from standard fractions to a ternary, or base 3, numerical representation. This means expressing every value along the interval as a decimal using only the digits 0, 1, and 2. When we map our first removal to the ternary scale, the middle third of the line consists entirely of numbers whose first ternary digit is a 1. Erasing the next middle thirds in stage 2 corresponds exactly to removing all numbers with a 1 in the second ternary decimal place. The overarching rule emerges. The Cantor set consists exclusively of every real number between 0 and 1 whose ternary expansion contains no 1s, only 0s and 2s. Because every decimal place out to infinity offers two valid choices, 0 or 2, the total number of mathematical combinations is uncountably infinite. This uncountable infinity matches the exact cardinality of the original solid interval. The link between the number of points and physical length is completely broken. This document summarizes the formal properties of the Cantor set established by the proof. Property 7 states the measure of the Cantor set is identically 0, yet Property 8 confirms it remains uncountable. This dust-like set, with no contiguous length, holds just as many points as the unending continuum of space. In real analysis, physical geometry is an illusion. The true architecture of the infinite must be measured by mappings and strict logic, not physical lengths and bounds.